Hello, my name is Michael Sliwa, and today we are going to be discussing two problems related to reaction mechanisms, the first of which being draw a reaction mechanism for the reaction of 1-bromo-3-methylcyclohexane with sodium cyanide in ethanol, which will be our solvent, and we'll get into that in a second here. Following that, we're going to be writing out a text description of the reaction mechanism, giving the UPAC name for the product. And that is going to be a bit of a paragraph, but again, we have to first, of course, draw our reaction to be able to do that. So in order to start this problem, we're going to go ahead and first start by drawing the molecule that we're going to be working with here, which is a 1-bromo-3-methylcyclohexane. As we know, 1-bromo means that we're going to have a bromine on the 1 carbon, and 3-methyl means we're going to have a CH3 or a methyl group coming off of the 3 carbon. And following that, we have cyclohexane, which tells us we're going to have an hexagon shape, not octagon. It will be hex, so, 6 sides. Hexagon. So we're going to first start by just drawing the original molecule, which will look a little bit like this. Like I said, we're going to have our 6-carbon ring in the shape of a hexagon. We can kind of predetermine where we want our 1 group and our 2 group and our 3 group, all things like that. So I'm going to go ahead and number this really quickly just for clarity's sake. So 1, 2, 3, 4, 5, 6. And we could go ahead and start adding our groups now. So at the 1 position, we're going to have a bromine or a bromo, which will look like that, and at the 3 carbon we're going to have a methyl group. So to kind of clean it up, I'll go ahead and remove the numbers and draw this a little bit nicer, but it will be the exact same molecule. So there it is, a little bit more cleaned up so that it's easier to see. And now we're going to be looking for a reaction with sodium cyanide, which we know is going to be Na with a kind of hidden plus, and a Cn, which is cyanide. So really just we're looking at NaCN. And what's going to happen here is that this is kind of a spectator ion, so we really don't have to worry about it, but we can't just have Cn minus sitting in solution, so we could include it just to be a little bit more specific. But we're going to go ahead and draw our reaction arrow here. And, it doesn't really matter what goes on the top or the bottom. Usually, though, we like to put our reacting, substance at the top of the arrow. I mean, that's just personally how I like to do it, but again, it could go on the bottom. But what I'm actually going to do is go ahead and put our solvent, which is ethanol, on the bottom of this, and that's just going to be a little bit something like that. So we have, a carbon here, and then we have an OH group all the way down here. And this is ethanol, or, just an alcohol in general. And we're going to talk about this a little bit later, but this is actually going to probably most likely affect the way that our reaction carries itself out. So now to look at this from the perspective of an organic chemist, we kind of have to look here at our alkyl halide, which is going to be, this whole big compound, the 1-bromo-3-methyl cyclohexane, that is going to contain this halogen, Br. So first of all, before even looking at this thing any further, we know that our bromine here is going to be a good leaving group, and that's due to the fact that right now it actually has a full octet, including the bond. So that'll look a little bit something like this, and what's going to actually end up happening as we go through this reaction is this bromine is going to get the full octet on the actual atom itself instead of the, being in a bond, which is going to allow it to leave the atom. And, it won't be a part of it anymore because it wants to, leave, I guess, as we've been saying here. So yeah, we have this arrow here. Bromine's going to be our leaving group. And also, we have to take into account this right here, which is a carbon that is being attached to the bromine. And basically at this bond here, we have to determine which degree of alkyl halide this is. So, if we kind of draw examples of each, we could have a primary alkyl halide in which bromine is only bonded to one other carbon, which would be over here. We could have a secondary alkyl halide where the bromine is actually going to be bonded to 2 different carbons. So there's our central carbon, there's 2 other carbons right there. Or we could have a tertiary alkyl halide, which could look a little bit something like this, where our bromine, the carbon that the bromine is bonded to 3 different carbons. So again, this is going to be a primary, secondary, tertiary. So if we look here, we actually have a bromine bonded to a carbon that's bonded to 2 other carbons. So we know that this is going to be a secondary alkyl halide. So now we're going to go ahead and look at our nucleophile here, which is this NaCN. Really, we're more focused on the CN, and we want to know if it's a good nucleophile. So the way that we could do this is by looking at the conjugate acid of this base here, and that would be HCN. And we know that the pKa of HCN is going to be around 9.2, which means that the conjugate acid of this weak base is going to be strong, and it's going to be a good nucleophile. So now that we know that this is a good nucleophile, we could go ahead and move down to our solvent, the ethanol, and look at it and see if this good, strong nucleophile is going to be solvated by this solvent. So solvation really only occurs if we have a polar protic molecule, and usually the way that I do this is just by looking if there's a H shown in the chemical formula here, or I guess more or less this would be the line structure. But anyway, if there's a visible hydrogen, 9 times out of 10, pretty much all the time that I've seen personally, it usually turns out to be polar protic, which will solvate. So yes, we have a polar protic solvent here. An example of a polar aprotic solvent could be something like diethyl ether, which again, you don't really have that visible H or hydrogen that you see here. But we're not worried about that. We're going to be looking in terms of this polar protic solvent that we have in front of us, which I also said would solvate the strong nucleophile. Right, so we have this here, right? Our nucleophile is going to be solvated, so it's going to go from a good nucleophile to a weak nucleophile. And basically all this is telling us is that instead of having a simple one-step reaction mechanism, which would be SN2, in which both our alkyl halide and also the nucleophile are included in the rate law, we're actually going to have an SN1 reaction, which is going to be stepwise with an intermediate. So like I said, stepwise, and we're going to have an intermediate. And the intermediate here is actually going to be something called a carbocation, and I'll go ahead and draw one of those as well. But I'm going to go ahead and clean up this a little bit, make it a little bit easier for us to start drawing this reaction in a way that's easy to see kind of what's going on here. So starting back here with our original molecule, I'm going to go ahead and draw this back in, our nucleophile, and also our solvent. And we could go ahead and get to work now that we've determined that this is an SN1 mechanism. So in an SN1 mechanism, what's going to happen is our leaving group, bromine, is going to go ahead and leave first before anything else comes in. And we're going to be left with this intermediate carbocation, which if I draw, in relation to this first structure, will look a little bit like this. Instead of having this bond all the way over here with the bromine, we're actually just going to have a positive charge, because right here we're going to have a carbon that has now lost 1 electron, since, as I said before, when that bromine leaves with the electrons from the bond, it's going to go from, it normally has 7 valence electrons, but it's going to take, that extra electron it's sharing here with the carbon from the bond and take it with it, which again, if we have 1 less electron, obviously we're going to have a positive charge. And of course this bromine is going to be bromide, which is negatively charged because it has an extra valence electron. We could also kind of look at this in relation to the undrawn hydrogen that's actually bonded here and see that we have 1, 2, 3 bonds to carbon, which usually likes to make 4 bonds, and that would mean that it has 3 valence electrons when, it usually, to be quote-unquote happier in its normal state, wants to have 4 valence electrons on it. So again, that's why it kind of gives that positive charge. And of course, we still have our methyl group over here. Nothing is going to happen with this. And going on from here, we kind of have to look at what we're going to end up at the product end of this whole reaction after the intermediate. So we have this positive charge here, which, isn't very happy. It wants to have something come in and make it neutral, which is, a lot lower energy. So what we first have to look at is actually what the structure of our CN molecule is here in the form of a Lewis structure. So as we know, carbon likes to make 4 bonds because it has 4 valence electrons, and nitrogen likes to make 3 bonds because it has 5 valence electrons. So what we could go ahead and draw in here is a triple bond between these 2 molecules, and from here go ahead and fill in our electrons, and the carbon is going to be more electronegative than the nitrogen, so the negative charge is going to reside on the carbon, and that is where our electrons are going to be coming from. So again, we have a lone pair of electrons that are going to be transferred off of the carbon right onto this positive charge, and what this is actually going to do is form a new bond altogether. So when drawing this final structure, we're going to have the same cyclohexane shape. we're still going to have our methyl group at the 3 position, but instead of having a Br in this bond right here, we're actually going to create a new bond with cyanide, which will look a little bit like that, and this is actually going to be our final product of this reaction. So making this distinction about the carbon being the one to actually donate the electrons to the bond here, we can actually go ahead and draw the same exact structure a little bit differently. And the way that this would end up looking, you know, if we're looking at this more realistically, is that the bond is actually going to be formed here, you know, with the carbon and then the still triple bonded nitrogen, since, you know, this electron pair all the way over here, you know, comes from that carbon. The carbon is making the bond and donating that pair of electrons to make the bond in the first place. You know, nitrogen is still attached to the carbon in the same exact way. And of course, we would still have the methyl. I just didn't draw it in, but yes, that would not change, of course. But that's just a little bit of extra information here. That's not exactly necessary, but good to know where your electrons are coming from to neutralize that carbocation intermediate that we found here. So now we've pretty much completed everything that this problem entails, and another good thing we could do is actually go ahead and name this molecule that is our product molecule right here. So we're going to start by naming at this cyanide group here. Go 1, 2, 3. And since right here we have a group that would be a carbonitrile, we could go ahead and start kind of naming this thing in terms of that. So usually this will go at the end of the name when UPAC naming conventions are taken into mind or into account. So we're actually going to start off here with, you know, naming the methyl in our UPAC name. So that would be 3-methyl cyclohexane. Because again, we still have a cyclohexane. Nothing has changed since, you know, this first name that we were given up here. And it will also be a 1-carbonitrile. So that is a UPAC name of this chemical structure right here, or this line structure, or just this molecule in general. So at this point, we've successively drawn a reaction mechanism for the reaction of 1-bromo-3-methyl cyclohexane with sodium cyanide and ethanol. And also another thing that's really important to note here is to go ahead and do some housekeeping and go ahead and keep track of where this sodium ion is going to be throughout the reaction. So this is something that we can write in if we want to. You know, we may or may not, but for clarity, I'm going to go ahead and show it. So even at this step right here, which would be kind of in here, I don't really want to draw an arrow, but it should be up in this area. We would have plus Na plus, because this counter ion, or this, you know, spectator ion that's not really doing anything, is still in solution when we're doing this reaction and carrying it out. And at the end here, at the products part, we also, you know, had this Br, this bromine, now bromide group leaving here, so that would now be in solution, and that would actually bond with this sodium cation, which would end up giving us, in our products, an NaBr, or a sodium bromide, however you want to say it, but you would also have that in your products. And I guess technically you could also say here that you have a Br minus kind of floating around the solution, and then they come together in the end. But that is basically that. And as I said, we've completed this reaction. We've determined which mechanism it'll go by, which is SN1, because of, you know, it being a secondary alkyl halide and also having a polar protic solvent, which is going to solvate the strong nucleophile and make it weak, which will be here, this nucleophile, the cyanide. And without talking too much to death, now we could go ahead and take this name that we got here and use it on this next part of the problem, which is writing out a text description of the reaction mechanism and giving the UPAC name for the compound. So the first thing that we have to keep in mind is the fact that we have this reaction here, and that this is going to be our reaction mechanism. So we have this original compound here that's going to be part of the mechanism. We have the sodium cyanide, which is going to be part of it, and the ethanol, which is the solvent. So we're going to start out by saying a little bit something like this. So we would start out by saying here that 1-bromo-3-methyl cyclohexane is allowed to react with sodium cyanide in a ethanol solvent. So that is basically just putting into words here kind of the problem that we have and kind of showing this whole reaction as well, without getting into any more of the other steps yet. So first we're going to talk about what our first step would be. So we would say the first step will be the breaking of the bond between the first carbon, or this carbon that's going to be attached to the bromine or the bromide at this point, between the one carbon and the bromine. We also want to specify something here, that the electrons from this bond are going to be going to this Br that is going to be leaving. So we would say something along the lines of, with the pair of electrons from the bond going onto the newly formed bromide ion. And we could kind of specify that here by just saying Br minus, but again, that's kind of what we're talking about when this leaving group is going to be separating itself in the first step of the reaction. So then next we have to talk about the second step in this reaction, which is going to have to do with this pair of electrons attacking this new carbocation that we formed from the bromine being the leaving group. So then we'll say something along the lines of, next, the lone pair of electrons on the cyanide's carbon will attack the positive charged positive, probably should have spelled that correctly, positive charge on the carbocation. Then we could talk about what this actually will do. So we could say something along the lines of, this will form a new bond between the cyanide carbon, because remember again, we specified on the other slide that when we look at this thing here, that this is going to kind of look like that, when in reality most of the time we're going to draw something that looks more like this. So it's actually the carbon that's being bonded, so we need to specify that in our answer or our text description here. And then we also have to specify where it is, and with the first position carbon on the cyclohexane ring. So we've stated all of that. Then we just have to state the product that we get, which is going to be naming this, which we also did on the other slide, which is 3-methyl-cyclohexane 1-carbonitrile. We could say the resulting product is a 3-methyl-cyclohexane 1-carbonitrile. So this is our entire text description written out. As you can see, we've named basically every step that's involved in this entire process, and I'll go ahead and go through that very quickly. So in the first sentence, we say 1-bromo-3-methyl-cyclohexane is allowed to react with sodium cyanide in an ethanol solvent. So that's our first sentence. We have our alkyl halide here, which we named on the other slide, which would be the 1-bromo-3-methyl-cyclohexane, which is allowed to react with sodium cyanide in an ethanol solvent. So we have all of that. From there, in the second sentence, we're going to go ahead and say what happens here. So, the first step, this bond right here between this carbon and this bromine is going to break which allows a bromide, that's going to be newly formed to break off into solution, and it's also going to take the electrons from that bond with it. In saying that, we also kind of allude to the fact that we're going to have a positively charged carbocation, because since we're taking an electron away from this already, stable carbon that is, quote unquote, happy, now it's going to be sad. It's going to be missing an electron and not have enough in relation to the amount of valence electrons it's supposed to have, which is 4, and here it only has 3. So then we talk about that here in the second sentence. The first step will be the breaking of the bond between C1 and the Br, with the pair of electrons from the bond going onto the newly formed bromide ion. And then in the next sentence, we say next, the lone pair of electrons on the cyanide's carbon will attack the positive charge on the carbocation, which we can see here. So we have our pair of electrons on the carbon in the cyanide here, which I explained up here with this Lewis structure, why that is. And we go ahead and we move those electrons right onto this positive charge. And what ends up happening, and this is the sentence we end up forming here, that says this will form a new bond between the cyanide carbon and with the, carbon in the 1 position on the cyclohexane ring. And again, that is what we see, and we have our product. And again, the last step is just to go ahead and name the product and say that the resulting product is a 3-methyl cyclohexane 1-carbonitrile, which is the name that we determined here. So that's basically the entire problem. That's drawing the reaction mechanism and then putting it into words. So hopefully you can follow along with that, and I hope you enjoyed this video.